Hello, and welcome to our video presentation for our IS108 Intelligent Systems final project. We are Group FH1, and today we are excited to showcase our predictive modeling application, Crypto Predict Business Intelligence. Our team consists of Prince Gonzalez, myself, Angela Lois Eicalo, and our lead developer, Van Renfred Otakan, who will walk you through the system demonstration later in this video. Our project is a comprehensive business intelligence tool engineered to classify and predict trading signals for the highly volatile cryptocurrency asset, Dogecoin. Let's start by looking at the business problem we are addressing. Traditional financial assets are valued based on cash flows and corporate fundamentals. However, cryptocurrency markets are exceptionally speculative, highly volatile, and heavily driven by retail sentiment. This makes predicting exact, continuous price targets incredibly noisy and unreliable. To resolve this, our application treats trading as a binary classification task. Instead of forecasting a specific price, we classify whether Dogecoin is in a buy state, meaning the price is expected to rise in the next interval, or a sell state, meaning the price is expected to remain stable or decline. This binary signal approach provides clean, actionable intelligence for quantitative traders and portfolio managers looking to manage risks. To build a robust system, we developed a structured 5-stage predictive modeling pipeline directly inside our application. It begins with raw historical market data ingestions. We then feed this into an automated feature engineering engine that computes standard techniques. To build a robust system, we developed a structured 5-stage predictive modeling pipeline directly inside our application. It begins with raw historical market data ingestions. We then feed this into an automated feature engineering engine that computes standard technical indicators like moving averages, RSI, and MACD metrics. This is followed by chronological splitting and standard scaling normalizations to ensure no data leakage occurs. Finally, the processed data is trained across k nearest neighbors, support vector machines, and an artificial neural network, concluding with our comparative validation dashboard. Our system processes a total of 2,760 daily historical records of Dogecoin paired with Our system processes a total of 2,760 daily historical records of Dogecoin paired with Tether. Beyond raw exchange data like open, high, low, close, and volume, we engineered advanced indicators to capture momentum and trend changes. First, a 14-period simple moving average to establish macro trends. Second, the relative strength index to capture overbought or oversold momentum levels. Third, the moving average convergence divergence or MACD alongside its signal line and histogram to isolate trend crossovers. And finally, an autoregressive lag feature representing the previous period's closing price. This forms a robust 11-dimensional feature space. Before training our models, rigorous preprocessing is executed. First, we drop the initial warm-up periods. Before training our models, rigorous preprocessing is executed. First, we drop the initial warm-up periods required to construct our technical indicators to remove empty values. Second, because we are dealing with sequential time series patterns, we employ a strict chronological 80-20 train test split instead of random shuffling. This results in exactly 2,196 training rows and 550 completely unseen testing rows. Finally, we apply Before training our models, rigorous preprocessing is executed. First, we drop the initial warm-up periods required to construct our technical indicators to remove empty values. Second, because we are dealing with sequential time series patterns, we employ a strict chronological 80-20 train test split instead of random shuffling. This results in exactly 2,196 training rows and 550 completely unseen testing rows. Finally, we apply standardization scaling. This normalizes our data so that all features have a mean of 0 and a standard deviation of 1, preventing high-volume metrics from overwhelming our calculations. I will now hand over the presentation to Prince, who will walk us through our machine learning model implementations and analytical results.
Thank you, Angela. Let us dive into our model architectures, starting with our first classifier, the k-nearest neighbors model, which is an instance-based local clustering classifier. We configured our KNN with 5 neighbors, using Euclidean distance to calculate similarity in our standardized feature space. During evaluation, the model identifies the 5 historical days most similar to the current market condition and takes a majority vote to assign either a buy or sell signal. So this allows the model to successfully capture recurring local liquidity blocks and sudden momentum surges. Our second model is the support vector machine, optimized for maximum margin hyperdimensional separation. Because cryptocurrency price distributions are highly nonlinear, a simple straight line boundary cannot separate the classes. So we utilize a radial basis function, or RBF kernel, which mathematically projects our noisy price indicators to an infinite dimensional space where they can be cleanly separated. So we set our regularization parameter to C parameter C to 1.0 to balance the boundary smoothness with training classification errors, allowing the model to construct a highly generalized decision boundary. Our final model is a deep feed-forward artificial neural network built using TensorFlow and Keras. It consists of 11 input neurons, 2 dense hidden layers of 64 and 32 neurons using the ReLU activation function to model complex interactions, and a single sigmoid output node to output the final signal probability. So the network is trained over 20 epochs with a batch size of 32 using the Adam optimizer and binary cross entropy loss to evaluate and minimize prediction errors. On our unseen independent test dataset of 550 observations, we extracted concrete comparative metrics. So our KNN model achieved an accuracy of 51.82%, a precision of 52.87%, a recall of 33.45%, and a F1 score of 40.98%. The SVM model returned an accuracy of 49.82% with a precision of 47.37%, but suffered a severe recall collapse down to 3.27%, yielding an F1 score of 6.12%. The ANN model achieved a generalized accuracy of 49.82%, which reaches up to 52% across random weight variations, a precision of 49.64%, a recall of 25.09%, and a F1 score of 33.33%. So let's analyze why these numbers are occurred. Next, so these results highlight 3 critical technical realities. First, our accuracy performance hovering around 50% to 52% reflects the standard efficient market hypothesis and random walk behavior in cryptocurrency markets. Volatile assets like Dogecoin cannot be predicted using lagging technical price indicators alone. Second, our RBF SVM suffered a margin collapse, classifying almost every test instance as sell. Because the data is highly noisy and overlapping, the SVM hyperplane collapsed to the background majority class to minimize training errors. Third is our KNN achieved the highest balance F1 score of 40.98%. This indicates that cryptocurrency market shows localized momentum clusters which instance-based models like KNN can successfully exploit. To make these complex analytical insights highly interactive and usable for business decision makers, we built a fully integrated business intelligence dashboard. Rather than interacting with raw code, users can import datasets, adjust parameters, train models, view metrics, and run custom market values in a live inference sandbox. I will now turn the presentation over to our lead developer, Red, who will conduct a live walkthrough of the running application.
Thank you, Prince. As you can see on the screen, this is our functional crypto predict business intelligence application. Our user interface is divided into a sidebar navigation panel containing our 5 core pipeline steps and a main operational dashboard. I will start by clicking the Load Project Dogecoin Dataset button. Immediately, the system ingests the raw historical coin Dogecoin.csv file. It profiles the data in real time, displaying a neat tabular sample of the prices, calculating that we have a total of 2,760 total rows, and outputting a complete statistical summary showing the means, minimums, maximums, and standard deviations of our raw features. This guarantees full transparency before any modeling begins. Now, let's navigate to our pre-processing and feature engineering tab. Here, users can dynamically configure our technical loopback indicators. We set our simple moving average and RSI window to 14. Watch as I click the Run Full Pre-Processing Pipeline. In the background, our ETL engine handles missing values, engineers our 11 technical features, drops nulls, and chronologically splits our data. The application immediately displays our engineered sample table containing standardized values along with our training and testing matrix shapes, exactly 2,196 training rows and 550 testing rows across our 11 feature columns. Next, we move to the model training dashboard. This is where we configure our machine learning models. Users can tune hyperparameters live, such as changing the number of neighbors for KNN, modifying regularization parameters for SVM, or altering network layer neurons for our neural network. I will click Train All Models. The application initiates training on our 2,196 training rows. Our KNN model trains instantly, followed by our support vector machine and our multi-layer TensorFlow Keras neural network. Below, we can see the live training loss and validation loss curves plotted over 20 epochs, proving our models are fitting and optimizing in real time. Once trained, we navigate to the evaluation dashboard. Clicking Run Comparative Evaluation prompts the system to test all models against our independent unseen 550 test rows. The application displays our comparative metrics table side by side, matching the statistical values presented earlier. Underneath, we have generated interactive visual confusion matrices for each model. In the SVM matrix, you can visually observe the recall collapse we discussed, where it placed the vast majority of predictions in class 0. Meanwhile, the KNN and ANN confusion matrices show a much healthier distribution of directional signals. Finally, let's look at the live inference sandbox. This is where the application transforms from an evaluation tool into a predictive assistant. It automatically extracts the latest scaled record from our live feed to generate real-time signals. As of our latest run, all 3 of our trained models successfully output an anonymous cell signal based on current indicators. Below, the user can input custom student and course details to export the structured academic inference report directly to their local directories. I will now transition back to our presentation slides for our final concluding remarks. So to conclude our video presentation, we must address our system's core limitations and outline our future development roadmap. First, on limitations, historical price indicators are naturally lagging. They only reflect past price patterns. Furthermore, decentralized assets like Dogecoin are heavily influenced by external retail hype and social media postings that purely technical price indicators cannot capture. For future iterations, we recommend 2 key expansions. First, sentiment data integration. We plan to integrate a natural language processing engine that parses real-time text streams from social platforms like X and Reddit, converting crowd sentiment into a continuous momentum indicator in our feature space. Second, automatic hyperparameter grid searching. We aim to build a background hyperparameter tuning engine that systematically searches model parameters in real time to prevent issues like the SVM margin collapse. This concludes our presentation of our Crypto Predict Business Intelligence. Thank you very much for watching our video walkthrough.